This is part 2 of Unit 6, Lesson 1, using Riemann sums to find area under a curve. So in the last part of this lesson, we introduced the idea of accumulation of change and using areas to find a definite integral. And we talked about using Riemann sums and making rectangles to do that. So what we're going to do in this part of the lesson is go into that in a little more detail. So we're going to start with the general solution method for inscribed or circumscribed rectangles, which are known as our lower or upper sums. So what you want to do to go through this is you want to sketch the graph, and then you want to use our delta x equals b minus a over n to determine each subinterval. And as I said in the last video, this is going to be the width of the rectangles. And then we're going to compute where they fall on the x-axis and decide if we're doing left or right hand. We're going to figure out what x-coordinates we're using. Then we're going to find the areas, and the other part of our area, our height of our rectangle, is going to be y of delta, well, not delta x, but y of x at those points, y of x. And then we're going to do the summation of the areas. That's where we're going to use the summation notation and do the areas. Okay, so example 3 says, find the area A under the graph of 1/2 x plus 1 on the interval for 0 to 5 using geometry. Now here's what you can do if it's a nice shape that you can use. What I see here is that I have a trapezoid. A nice trapezoid. Here's one base of the trapezoid. Oh, we're going to 5. Here is the other base of the trapezoid. And I have this nice figure here. And here's the height of the trapezoid. So here's B1. Here's B2. And I have the height. The height is going to be 5 units long. And B1 is going to be where it hits the graph here. So I have to do f of 5. And I get 1/2 of 5 plus 1. So I get 7/2. And then for B1, I'm going to do the same thing. I'm going to do f of 0. So I'm going to get 1. Okay? So I'm going to put that all together. So my area is going to be 1/2 the height times B1 plus B2. That's the formula for a trapezoid. So my area is going to be 1/2 the height, which is 5 units, times 1 plus 7/2. And then it's just a matter of multiplying this out. So I get A equals 5/2 times 9/2. So I get 45 over 4 units squared. Whoops, that s is not supposed to be the exponent. So we could even write this that the area from 0 to 5 of f of x is 45 over 4. Okay, so that's, if you have a shape that you can definitely take the area of, do that, because it'll be exact then. And if you did this with rectangles, you're either going to have an overestimation or an underestimation. But because it was a shape we could work with, we can find the exact area under that curve. Okay, so here's how errors come up, as I was just mentioning in Riemann sum with example 4. Example 4 has us, we're going to do the left-hand sum, the right-hand sum, and then talk about what happens if we do it again with a different type of graph. Okay, so what we have here, and we're going to talk about this in more detail, we have a decreasing graph that's concave down. So we want to draw rectangles forming the left-hand sum shaded in blue. So what I'm going to do is we're going to let delta x equal 2. So each rectangle is going to be 2 units wide. So that's going to be one side of the rectangle right there. And we're going up to 6 here. Okay, so a left-hand side rectangle is the part it touches the curve will be on the left-hand side. So I'm going to draw a rectangle from there and over to there. And then the next one is going to be from where this side of the rectangle ends on the left to where it touches the curve and then straight down. Then my next one is again going to be on the left-hand side of that interval and down. And it turns out I only have 3 blue rectangles, so that's fine. So my area is going to be the width, which is 2 times, and the height of each one is going to be where it hits the curve. So the height of the first one is 8, plus 2 times the height of the next one is 7, plus 2, which is, don't forget that's this width down here, 2 times 5. So my area is going to be 16 plus 14 plus 10, which gives me 40 square units. And if you notice, this is an overestimation. And you can see that because I have extra area above each of these rectangles, especially right there. I'm barely using half that rectangle, really, a little more than half of the last one. So that is definitely an overestimation. So now what we're going to do in red is we're going to do a right-hand calculation using width of 2 again. So that means this time the rectangles are, the part that hits the curve is going to be where they end. And so here is the width, so the ending side. So this is the first rectangle. Here is the second rectangle. And here is the third rectangle. And if you notice, now I'm way under, especially in the last one. Don't even think I'm using a third of that entire area there. So my area is going to be, my width of my rectangle is still 2. The height of the first one is now 7. The height of the second one is now 5. And the height of the last one is only 1 unit. Okay, so adding these together, I get 14 plus 10 plus 2. So I only get 26 square units. So this is an underestimation. Okay, so I've already answered the next question, which is the left-hand sum is an overestimation, and the right-hand sum is an underestimation. Okay, so we see that when this is concave down and decreasing, that the left-hand sum is over, the right-hand sum is under. Okay, so now, again, this function is concave down, but it is increasing. So does the over and underestimation change at all? So we're going to start again with blue, and this time our width is 0.5, so it's still on the graph going to be 2 units, 2 of those units wide, but it's the actual value of that is 0.5. So my first rectangle is going to be at the beginning. Left-hand estimations are at the beginning of the interval, so it's going to be here. The next one is going to be here. And the last one is going to be here. Okay? So, finding these areas, I'm going to have area equals 1/2. That's how wide our region is now. 1 plus 1/2. Our next height is 4 plus our last height is 6. So this is going to be 1/2 plus 2 plus 3. So this ends up being 11 halves, which is 5.5. Okay, and our right-hand rectangles. So now we have the same intervals, but we measure on the curve where the interval ends. So we go across, our interval ends here. So here's our first rectangle. Here is our second rectangle. And again, we're over where we end. And there's our third rectangle. So as you can see, our blue ones are underestimations and our red ones are overestimations. So now our right-hand sum is going to be, our area is still going to be 1/2 unit wide, and now our first height is 4, our second height is 6, and our third height is all the way up here at 7. So we're going to have 2 plus 3 plus 3.5, which is 8.5. Big difference between the two. So our left-hand sum is now an underestimation, and our right-hand sum is an overestimation. Okay, so just summarizing this, how this works out. So we're going to look at the idea of whether the function is concave up or concave down, and whether it's increasing or decreasing. So let's do the concave down ones first, because they're the ones that we did above. So when the function was increasing, which was the second picture, what we saw was the left-hand sum was an underestimate, because the picture looked like this. So all our left sums were underneath the curve, and the right-hand sums were an overestimate. Okay? And then in our first picture, we had the opposite happen. We were still concave down, but we were decreasing. So the left-hand sums were an overestimation. See, our blue rectangles were over, and our red rectangles are under. So our left-hand sum was going to be an overestimation, because now from the left, we were always going to be above the rectangle. And I'm just putting the general shape of the graph there. And our right-hand sums were under. Okay, so on a decreasing function, so that'll look like this, for concave up now. Whoops, I put that in the wrong spot. I apologize. We're still concave down, so we're here. The left-hand sum is over. It's because we're looking like this. We are looking like this. There we go. And our right-hand sum is under. Okay. Now concave down. Let's start this way. I'm confusing myself. Okay. So our graph's going to look like that now for concave up and increasing. So our left-hand sums are going to be under, and our right-hand sums are going to be over. So when you do it the other way, our left-hand sums will be over the curve, and our right-hand sums will be under the curve. Okay, so we're going to finish this lesson up with putting together all the different ways we can use summing of rectangles to find area under the curve. We're going to do 4 different ways in this example. We're going to do our left and right hand sums, but we're also going to do a midpoint, and then we're going to end using the trapezoidal method, which I believe personally is the most accurate, because now you can have a slanted side that could somewhat follow the curve more like a tangent line than just straight horizontal lines across the curve. Okay, so example 6. The table below represents the velocity v of t in feet per second of a car traveling on a straight road over a 50-second time interval. We want to estimate the distance the car traveled over this interval using right-hand sums and left-hand sums, along with 2 different approximation techniques, the midpoint and trapezoid rules. Use the table along with the graph for your computations. So this is something we have done before, like we have found area under a velocity curve to determine the amount of distance traveled. So it's the same idea. So here's our table, there's our graph, everything's been plotted for us. So we want to use the left-hand sum, and they have L5 there, which means we want 5 partitions of equal length. So that's the first thing I have to figure out is what is my delta x. So I'm going to do this. We're going to do the same thing for both of these. So on the side here, my delta x is going to be my starting x, which is 0. My ending x is 50 seconds, and I'm going to divide that by the number of partitions I want, which is 5. So my delta x is going to be 10 seconds. That's going to be the width of each rectangle. Okay, so now let me do this in blue. I am doing a left-hand sum, and so that's at the beginning of the interval. The very first rectangle is going to be 0 because the curve hits the left-hand side at 0. So the first rectangle is 0. The second one is going to start here and go across 10 seconds. The next one on the left is there and goes across 10 seconds. The next one is clear up there and goes across 10 seconds. And then the last one starts there and goes across 10 seconds. Okay, so you just want to double check. We have 1, 2, 3, 4, 5 rectangles. Okay, so our left-hand sum with 5, that's a 5, not an S. I'm just going to write this as left L5. Is going to be our first rectangle, which is 10 times 0 plus 10 times, and I can get the values right from the table. At 10 seconds, I'm at 20. And at the next one, I'm at 20 seconds, I'm at 52. The next one, at 30 seconds, I'm at 80. And at 40 seconds, I'm at 77. So you can even pull the 10 out and just add all the numbers up together. So that's 229. And that's going to be a total of 2,290 feet. Okay? So now doing this again before I move everything, I'm going to do my right-hand rectangles in red. So that means I'm going to start on the end of the interval. So that's here, and draw it over. So the next red rectangle goes here. The next red rectangle goes here. The next one goes here. And then the last one is there. So there are my red rectangles. Okay, so let me just shade these in a little bit. I'll make it a little easier. So I have none there. There's my blue one. And then my red ones also include all this. So you can see in a curve like this, there's no perfect over or under part. It's some of both. Okay, so now moving this so I have some room. My right 5 divisions, my interval is still 10. I'm going to pull that out because I'm just going to multiply 10 each time. So my first height is going to be 20, plus my next height is 52. My third height is 80. My fourth height is 77. And that last height at 50 is 74. So adding all those numbers together, I get 303. Multiplying by 10, I get 3,030 feet is how far my car went. Okay, so you can definitely see that we have a problem here. A lot of times what you do then is you would average these together. So you would do 2290 plus 3030 and divide them by 2. So this would be 5320 over 2. So we would report an area or a distance of 2660 feet. So you normally do both. Okay, so a way around that is you could use the midpoint sum. So we're starting with the same graph again, but now we're going to have it cleared off of our rectangles. And the first rectangle has been drawn for you. If you notice, our interval hasn't changed. It's just where the height is different now. So our first rectangle, and I'll use green for this, is going to be right here as is shown in the picture. And then the next rectangle, the midpoint is going to be right there. So there's my second rectangle. My next one will be right here. And a lot of times where more of the error is introduced in the midpoint one is estimating exactly the value. If you're not given the function itself, what that y value is, because it may not be in the table. It just so happens for this example we put all these values in the table. So again, 1, 2, 3, 4, 5 rectangles. So our midpoint, so I'll just call this MP5, is going to be, our width is still 10, and the first height is going to be at 5, and these values, as I said, are in the table. So that's 14. The next height is 28. The third height is 70. The fourth height is 86. And the fifth height is 70. So you can see all of the 5s are in here. So there's the 14, 28, 70, 86, and 70 at 45. Okay, so simplifying this, I get MP5 is equal to 10. Adding those numbers up, I get 268. So I get a value of 2,680 feet. And if you notice, that is really close to what our average was of the left and right hand sums. So now, let's do it using trapezoids. So in the same picture, I'm going to do trapezoids, and I'm going to do those in gold so we can see them. So how you do a trapezoid is you connect the first point of the interval and the last point with a line, and then you have your two sides of your trapezoid there. Okay? Now in this case, one of the bases is going to be 0 because I have no height here. That's what's missing. That first one's a little hard to see because of that. But here's the next one. Here's the first base. Here's the second base. And then I connect these two like that. So there's my trapezoid. So again, my first base is here for the third trapezoid. My third other base is there. And I connect those to the endpoints on the curve. So for the next one, that becomes my first base. My second base is there. And then I'm going to connect these two. Whoops, that's a really bad connection. So I'm going to connect these two this way. And then again, that's my first base. My second base will be here. And then I connect those two. So you can see that for the most part, we're a little closer. So our areas are going to be, we'll call this T5, remember our area of a trapezoid, is 1/2 the height times B1 plus B2. And I'm going to point something out as we do this, and I'll rewrite it that way in a second. So I'm going to keep the 1/2 out because they'll all have a 1/2 and they're all going to have a 10. And then what I'm going to do is I'm going to show adding of the bases. So the first trapezoid, you're adding 0 and 20 for the two bases. The second trapezoid, you're adding 20 and 52. For the third bases, you're adding 52 and 80. For the fourth bases, you're adding 80 and 877, and then the last set of bases is 77 and 74. Now, what I want to point out to make some of this arithmetic a little easier is, except for the first and last base, you use every other base twice. There's two 52s, two 20s, two 80s, two 77s. The only ones that are different is the very first base and the very last base. So if you want to set this up, you can write it this way as a first step: 1/2 10 times, and then you have you wouldn't write the 0, but 0 plus 2 times 20 plus 2 times 52 plus 2 times 80 plus 2 times 77 plus 74. You can do it that way because trapezoids always work out that way. All right, so finishing this up then, I am going to have that my T5, sorry about that, my T5 is going to equal 5, half of 10, times, when I add those all up, I get 532, which gives me an area of 2,260 feet. So if you notice, you can either average the two, you can use the trapezoid method or the midpoint method to get the closest approximation of the area. Okay, so I already did that for the last question. I forgot that was the last question. So let me just write that work down here so we have it. So L5 plus R5 divided by 2 is going to be 2290 plus 3030 over 2. So that's 5320 over 2, which is 2,260 feet. And this is the same as the trapezoidal method. So we will do more practice of this in class, and I will answer any questions at that time.